Good afternoon, everyone. Welcome to the class in Operation Research. And guys, in today class, we'll start the concept of duality in linear programming. We'll discuss about this topic. So, guys, we have done so far how we can construct an LPP problem, and then once we are done with the construction of LPP mathematical problem, we learned how to find the solution of those problems by using either graphical method or by using simplex method. In simplex method, whenever in your constraint you have more than or equal to sign, then you'll introduce negative slack variable and you apply bigger method to solve it. I hope you remember all these concepts we discussed till now. Now the question arises, what you gonna do now? What we're going to discuss now. So now we're going to talk about the concept of duality. Okay, what is the concept of duality, sir? So concept of duality basically means that every LPP problem, whichever LPP problem we are trying to solve. So every LPP problem, I'll call that as a primal. So I will call all LPP problem as in primal, and this primal I can convert into dual. Okay, so every LPP problem you can transform into another form of LPP problem. Okay, that is what I'm trying to explain here. That every LPP problem which we called as primal, okay, it can be transformed into dual. Okay, so which can be transformed into dual, and this concept of converting any LPP problem into a dual form, it to convert that into dual form or to convert the dual form of an LPP problem to primal form. This concept is called concept of duality. So you will say, sir, okay, sir, I understood you can convert an LPP problem into another form of LPP problem. If you solve that also, or if you solve this also, you'll get the same answer. All that I understood. But what is the need of doing it? Now the question is why you should do that, sir. So the reason why we do this, so the importance of duality concept, when I talk about the importance of duality concept, why we use this duality concept, the importance of duality concept is mainly because of two reasons. It's mainly because of two reasons. It's mainly because of two reasons. What are those two reasons? So please understand those two reasons so that you will understand the need of using duality. So if the primal, if the primal contain lot of constraints, if the primal contain lot of constraints, so imagine if your primal is having lot of constraints, so you know that, right? How many constraints you have, that many slack variables you have to introduce, negative or positive. So all together, if you try to solve any LP problem having a lot of constraints, then you can understand the complexity the problem will tend to be. Okay, even then if there are two decision variable having lot of constraints, so if you are solving by graphical method also, you have to draw that many lines, and then finding the feasible region among all those lines satisfying all the condition would be very big task. Solving by LPP problem again would be solving the LP problem by simplex method, again it would be headache. Okay, because that meant that many, what you call, the slack variables you'll introduce, and then if they are more than or greater than, then you that many you'll have artificial plus positive slack variables all together. It tend to be that much complicated that solving would be big headache. So if the primal contain large number of constraint and small number of variables, so imagine if your primal constraint contain large number of constraint and small number of variables. Okay, and small number, only two variables are there, and suppose constraints are five. Okay, so it would be better, no, if I can convert that. So having, imagine, instead of that, what is better? Two variables and five constraints, or five variable and two constraints. So I hope you will say that five variables and two constraints. So that is what we do when we convert the primal into dual. So the if the primal contains large number of constraints and small number of variables, okay, then the labor of computation can be reduced by converting it into dual problem and solving it. So if the primal contain large number of constraints, small number of variables, then the labor means the time, the effort, what you do to solve the problem, then the labor of computation, then the labor of computation, then the labor of computation can be considerably reduced. The labor means the time what you take to solve it. Then the labor of computation can be considerably reduced, by converting it into dual problem, by converting it into dual problem, and then solving it, solving then uh, if the next reason why we need to write the problem in the primal of the problem to dual form. What is the need? The first need you understood. Imagine it is having lot of constraint and very small variables. If you can convert into dual form, automatically the number of constraint will transform into number of variable, and number of variable will transform into number of constraint. That is what we do in duality. Next reason is that the interpretation of dual variable from the cost or economic point of view prove extremely useful in making future decision in activity being programmed. So that is theoretical explanation given. That imagine whenever you are solving a problem, and please understand what happens. No, if your primal is having an objective function called minima, so when we convert into dual form, then the objective function become maxima. Okay, so that way, imagine my intention as in running this company. My intention is to work on profit, but the kind of mathematical setup what I got was there in the form of cost. So then automatically, if your mathematical setup was giving you data on the basis of cost, automatically your objective function would have been become minimization of cost. But in more than minimization of cost, I was more interested on the profit data. So I need to convert the minima function into maxima function. Okay, so that way what we can do, we can convert it into dual. So when we convert into dual, minima function become maxima function, vice versa. While if you had a maxima function, then you could have converted into minima function. Okay. Now I know that many of you would not be understanding what sir is talking about. So we'll try to solve one problem to make you understand. So how to now the question is, sir, okay, I understood, sir, what you are telling, that if you have lot of constraint and very few variable, then better to convert into dual form. So whenever you convert into dual form, what happens now? Whenever you're converting to dual form, when I talk about formation of dual problem, so what happens whenever you convert into dual form? So your objective function, which is in maxima, will turn into an objective function having minima, and the number of constraint of the objective function will become equal to the number of variables of the objective function there. So the primal the RHS of the primal will become the coefficient of the objective function of dual, while the while the while the while the coefficients of the objective function of dual will become the RHS of the primal. So that way we convert them. So when we talk about formation of dual problem, so first of all, we need to bring the problem to canonical form. So before conversion, whichever problem you see, it should be in canonical form. This you need to convert. You need to make sure your problem is in canonical form. Canonical form basically means that if your objective function is in maxima, then your all the variables of your constraint should be having less than or equal to sign. That is called canonical form. While your objective function is in minima, suppose if your objective function is in minima, then all your constraint should have sign greater than or equal to. Okay, so you can understand this is called canonical form. So first you need to make sure the primal, so you are converting now primal into dual. So first you make sure that the primal is in canonical form. Okay. So then what we do, the next part, what we do, we change the objective function of maximization in the primal into minimization in the dual and vice versa. That is the first thing what we do. Next thing what we need to take care is that the number of variables in the primal will be the number of constraint in the dual. This I already told you, and vice versa. Okay, third thing, that the cost coefficients in the objective function, okay, of the primal will be the RHS constant of the constraint in the dual and the vice versa. So if you're not understanding this part, I'll make you understand. I'm just telling you the theory part. The next part, in forming the constraint for the dual, we consider the transpose of the body matrix of the primal problem. Okay, and then the next thing is that whenever we see the variables and in the problem decision variables, they should be non-negative. That is always be there. Doesn't matter you write in primal or dual. After all, it's a LPP form, so it should always the when you see the your decision variable should always be with non-negative form. Okay, and imagine if the variables in the primal is unrestricted in sign, then the corresponding constraint in the dual will be the equation and vice versa. So mainly these are the following points which we need to remember whenever you are trying to solve the problem. Okay, so I'll instead of talking theory, let me first give you an example to understand what I mean to say. Suppose this is the problem. So write the dual. Okay, write the dual of the following. Write the dual of the following. No matter how much theory I write in this subject, you'll not understand till the time I actually don't do the problem. So write the dual of the following primal. Write the dual of the following primal LP problem. Okay, let the write the dual of the following primal of LPV problem. Suppose your objective function is maxima of z is equal to x1 plus 2x2 plus x3, okay, subject to constraint is given 2x1 plus x2 minus x3, okay, that is less than equal to 2. Okay, then next constraint minus 2x1 plus x2 minus 5x2, okay, that is minus 5x3, that is so minus 2x2 plus x2 minus 5x3 is greater than or equal to minus 6. Third thing is that 4x1 plus x2 plus x3, okay, that is less than equal to 6. Okay, then x1 x3 that is greater than equal to 0. So this is the problem, guys. Now this problem I want to convert this into dual form. Okay, so guys, this is your problem, and this problem I want to convert into dual form. So before I want to see the dual form of this, although it have three variables and three constraints, but even then, just a problem I want to show you in the dual form. So that is what I'm trying to do here. So here what you need to understand, the first of all, this problem, is this in canonical form or not, you have to check that. Okay, if you see the objective function is maxima, so all your constraints should be less than or equal to, you can see this is less than or equal to, but this is not in less than or equal to. Can you understand this? So this is greater than or equal to. So first you need to write the problem in canonical form. If this is objective function, if this is your objective function, so I'll write this. So since the problem is not in canonical form, since the problem is not in canonical form, since the problem is not in canonical form, so so writing this problem, in canonical form, so I'm writing this problem in canonical form. So I'm writing this problem into canonical form. So if I write this problem into canonical form, so then I'll write my object question maxima of z is equal to x1 plus 2x2 plus x3 subject to constraint that is 2x1 plus x2 minus x3 is less than equal to 2. Okay, then this you can see, no, this is greater than equal to. So how will I convert into less than or equal to? Change the sign. So 2x1 minus x2 plus 5x3 is less than or equal to 6. And this is 4x1 plus x2 plus x3 is less than or equal to 6. Where x1, x2, x3 that should be greater than or equal to 0. Clear? Any doubt, anyone? So this way you write the problem into canonical form. Any doubt, anyone? So you write down this problem into canonical form. Then what you will do? Once you write the problem into canonical form, to convert this into dual, count the number of constraints. Three constraints are there. Introduce three dual variables. So let W1, W2, and W3 are dual variables. So why sir, why W1, W2, W3? Because that variables, that decision variables of the dual form will totally depends upon the number of constraint you have. So here I have three constraints, so I'll introduce three dual variable. Is that okay with you? Can you understand this? Okay, then what would be objective form? Then in dual form, then I'm writing them in the dual form. Then in the dual form, your objective function will be minimization of z dash, because first one is maximization of z. So please remember guys, whenever you're writing the primal into dual form, then your objective function, if that was maximization, that will turn into minimization, while if your objective function was minimization, that will turn into maximization. I hope you understood this. So now your objective function will be minimize of z dash equal to, you introduce three dummy variables, right? W1, W2, W3. So you will write them. So when you are writing them, okay, when you're writing them, so you write no W1, then you write W2, then you write W2 in some plus minus sign. You'll use yes or no. You use right plus minus sign. You use some coefficient, no. So please remember that the RHS, please remember that the RHS of the primal will become the coefficient of the objective function. Can you understand? 2W1 plus 6W2 plus 6W3 will be your objective function. Can you understand this, guys? So that is what I said before, that the cost coefficient in the objective function of the primal will be the RHS constant of the constraint of the dual and the vice versa. Okay, can you understand this? So the RHS of the primal will become the cost coefficient of the dual, and here, so and you need to understand here guys, that the RHS of the primal will become the cost coefficient of the objective function of dual, and the cost coefficient of the primal, the cost coefficient of the primal will become the RHS of the dual. So this one, this two, this one, all this will become the RHS of the dual. Can you understand this? So this is minima, no? So the constraint you will use is greater than or equal to. You use three constraint greater than equal to. So the cost coefficient 1, 2, and 1, 1, 2, and 1. So the So guys, can you see this? The what I was telling you. Sorry for disturbing. So if you see this, the if you see the primal, the cost coefficient of the objective function of the primal will become the RHS of the dual. Okay, and the RHS of the primal will become the cost coefficient of the dual. Please understand this part. So this was your minimum objective function. So whatever was your cost coefficient of the objective function of the primal, okay, that was I was telling you. What would be the whatever was your cost coefficient of the objective function of the primal will become the RHS of the dual, and whatever was the RHS, whatever was the RHS of the constraint of the primal will become the cost coefficient of the objective function of dual. I hope this part you understood. I don't think anybody will have doubt on this. Subject to, then you'll write subject to, then you'll write subject to. When you write subject to, so now you write no the constraint, right? So how will you write the constraint? How will you write the constraint? So for writing the constraint, no, guys, what you need to do, what I said for writing the constraint, I said that that in forming the constraint of the dual, we consider the transpose of the body matrix of the primal. So again, I'm telling you what I said. I said that in forming the constraint of the dual. So I want to write the constraint of the dual. No, yes. So then, when you are writing the constraint of the dual, then we consider the transpose of the body matrix of primal problem. What is the transpose of the body matrix of primal problem? So, so what are the transpose of the body matrix of primal problem? You can see 2, 2, 4. So here three variable you introduce, no? So 2W1 plus 2W2 plus 4W3 is greater than equal to 1. Okay. Then this is 1, this is minus 1, and then 1. So then you again you write this. Then the next constraint will be W1. Okay, then minus W2, then plus W3 is greater than equal to 2. Okay, the third one you can see this, guys. What are your constraints? So you'll write minus W1 plus 5W2 plus W3 will be greater than or equal to 1. Can you understand this, guys? So and then after that non-negative string where W1, W2, W3 should be greater than equal to 0. So it doesn't matter you're writing primal or you're writing dual. When doesn't matter you're writing primal or you're writing dual. So your decision variable should always be non-negative. Clear, everyone? So this way you write the problem into dual form. This way you write the problem into dual form. This way you write the problem into dual form. This way, whenever we have a problem, we write down the problem into dual form. I hope you understood this. Very easy. Okay, right now, today class I will not solve this problems and all. So if we solve this problem or if you solve this problem, if you solve this problem, if you solve this problem, so you solve this problem, okay, find the value of x1, x2, x3, and you solve this problem, find the value of w1, w2, w3. That will remain the same only, guys. I hope you understand it. Okay. So then, okay, write down the next problem. If I ask you that find the dual, find the dual of the following LLP. Find the dual of the following LPP. If I ask you find the dual of the following LPP, so objective function is maxima of z is equal to 3x1 minus x2 plus x3. Okay. Then subject to, write your objective function subject to 4x1 minus x2 uh, is less than or equal to 8. Okay, then next constraint is 8x1 plus x2 plus 3x3 is greater than or equal to 12. Third one is 5x1 minus 6x3 that is less than or equal to 13. And then your x1, your x2, your x3 that should be greater than or equal to 0. This is the problem, guys. Now, guys, if you see your objective function that is in maxima, okay, so your constraint should be less than equal to, this is less than equal to, fine. This is less than equal to, fine, but this is not less than equal to. This is not in canonical form. Can you understand this, right? So this is what you need to do. Okay, the first, you see your primal, this we called as a primal. First, you see your primal. When you see primal, then you need to make sure your primal should be in canonical form. Okay, so since my primal is not in canonical form, so I'll write maxima of z is equal to 3x1 minus x2, 3x1 minus x2 plus x3 subject to subject writing it in canonical form subject to 4x1 minus x2. You can see there's no x3 here. So can I write x3 is 0 x3? Okay, you don't write also, that's fine. Simply I'm writing 0 x3. So 0 into any number is 0 only. That is less than equal to 8. This I can write as minus 8x1 because you know, no, you transpose and write. So better write in proper order. So minus 8x1 minus x2, okay, minus 3x3, okay, that is less than or equal to minus 12. Okay, then this is 5x1 plus 0x2 because there's no x2 here, minus 6x3 is less than or equal to 13. Okay, and where your x1, x2, x3 is greater than or equal to 0. Can you understand this? I wrote them in canonical form. So writing the problem in canonical form. So writing the problem. So writing the problem. Writing the problem in canonical form. Writing the problem in canonical form. Okay, so I wrote the problem in the canonical form, guys. So this was your problem. I wrote this problem in canonical form. Okay, guys. Can you understand this? I hope you understood. If your objective function is in maxima, then your constraint should be less than equal to. Yes, sir. I wrote, sir, in canonical form. Okay, sir. Then this once you write it in canonical form, guys, then this we called as primal. Then we call this as a primal. Okay, guys. So when we are trying to convert the primal into dual form, so when we are writing this into dual form, when you're writing this into dual form, then your maxima function we write in minima function. Write minima of z dash because this was z dash. So then the RHS, see the RHS of the constraint of the primal. Okay, so see the RHS of the constraint of the primal. Okay, so they will be the cost coefficient of the dual because here three constraints are there. So I'll use three non-dummy variable, three decision variable of the dual. So I can write 8W1 minus 12W2, okay, plus 13W3. Can you understand this? Introducing the three decision variables of that they are W1, W2, W3. Can you understand this, guys? Very simple. Okay, so RHS of the constraint of the primal will become the cost coefficients of the objective function of the dual. Okay, and then the cost coefficient of the cost coefficient of the primal will become the RHS of the constraint of the dual. So subject to how will you write? your variable, you know you have three decision variable, and you know that you're going to have three constraint. So write the transpose of the body matrix of the constraint. 4w1 minus 8w2 plus 5w3. Can you understand this? Hmm. See the objective function. The objective function is what? Max minima, na? The objective function minima. So what would be the sign of the dual? This would be greater than or equal to. And what is your RHS? RHS is the objective function, the cost coefficient of objective function of primal. That would be 3. Clear, guys? Okay. Then next one is this. This I can write minus W1 minus W2 plus 0 W3, that is greater than or equal to minus 1. Can you understand this? Okay. Third equation will be uh, 0w1 minus 3w2 minus 6w3 is greater than or equal to 1. Okay, guys, where w1, w2, w3 is greater than equal to 0. Can you understand this? Any doubt, anyone? Now I can write it this in other form. What I can write the same thing, I can write this. The better way of writing dual form, I can write this form as minima of z dash is equal to 8w1 minus 12w2 plus 13w3 subject to 4w1 minus 8w2 plus 5w3 is greater than equal to 3. This I can write as w1 plus w2 less than or equal to 1. Can you understand this? This I can write as minus 3w2 minus 6w3 is greater than or equal to 1, where w1, w2, w3 is greater than or equal to 0. I hope you understood this. So either you find the decision variable of your dual form, or either you find the decision variable of your primal form. So they will give you the same answer only. Can you understand? Anyone have any doubt? So we learn gradually. We learn first. We are learning how to write the primal into dual. So once we learned how to write the primal into dual, we'll try to do few problems to prove that the answer what you get in primal is equal to the answer what you get in dual. Anyone any doubt? Clear, everyone? Anyone any doubt with this? So we'll do this much, guys, today. We'll continue discussion tomorrow, and we'll try to understand more about the concept of duality. This was our first introductory session on duality. So how to write the same problem. Every primal has another phase. Like like we have another phase. So like the same way the equation, the mathematical equation of LPP can be written in the other way. So then the other way of writing is called as dual form. So you can solve the problem like same way and you'll get the same answer. Can you understand this, guys? Anyone, any doubt? Any doubt, anyone? We'll do this much today. We'll continue discussion next class. Anyone, any doubt, any question? So I'm ending the class, guys. Thank you, everyone. See you all on next class. Take care. Bye, everyone.